In this review, we'll provide some problems that involve the normal and tangential coordinates. Let's begin with this one. See if you can determine the velocity and the normal and tangential components of acceleration of the motorcycle when the time t is 1 second, if originally the motorcycle is at rest when it's at the origin. We'll take the increase in speed of the motorcycle along the path to be equal to 20 times t. See if you can get the results. Well, to solve the problem, the first thing we'll do is determine the velocity of the motorcycle. And to do that, we'll use this equation. A sub t is a function of time, so we set this equal to 20t and multiply it by dt, and then we can integrate both sides. On this side of the equation, I would integrate from t equaling 0 to 1 second, and on this side, I'd integrate from a velocity of 0 to a velocity v. When you carry through the integration, you get the answer of 10 meters per second for the velocity of the motorcycle. Obviously, the tangential component of acceleration can be found from this formula at the time t equaling 1 second, and it turns out to be 20 meters per second squared. Finally, we can get the normal component of acceleration by simply taking our value for the velocity of 10 meters per second and squaring it, and divide by the radius of curvature of the path, and that's equal to 20 meters. Gives us a component of 5 meters per second squared. This, of course, represents the change in the direction of the velocity vector, and this one, of course, is the increase in its magnitude. All right, now try this one. See if you can find the acceleration and velocity of this particle at the position s equaling 2 meters. If originally, the particle has a velocity of 3 meters per second. Well, to solve the problem, we'll begin by first finding the velocity of the particle when it reaches the position s equaling 2 meters. And to do that, we'll have to use this equation, the one that doesn't involve time, because after all, the increase in the speed of the particle is defined as a function of position. And now to apply the equation, we substitute for a sub t its value of 4s. We have ds here. And on the other side, of course, we have v times dv. Now we integrate each side. Here, from position s equaling 0 to a position of 2 meters. And on this side, from a velocity of 3 meters per second all the way to an unknown velocity v. If you carry through the integration, you get the result of 5 meters per second for the velocity. Now that we know it, we can find our components of acceleration. The acceleration in the tangent direction is determined from this equation. Simply put s equaling 2 meters in here, and you get the answer of 8 meters per second squared. The normal component, of course, comes from this equation, where we take our velocity of 5 meters per second and square it, and divide by the radius of curvature of the path, which is 2 meters. We get 12.5 meters per second squared. And so adding these two components up vectorially, we get our resultant acceleration, through the Pythagorean theorem, of course, 14.8 meters per second squared. That acceleration, of course, is going to be directed inward toward the curve. All right, here's our final problem. See if you can determine the normal and tangential components of acceleration when the particle is at the position x equaling 0 on this parabolic path. Well, to solve the problem, the first thing is to consider the tangential component, and of course that's equal to the increase in the speed of the particle here. That's represented as 6 meters per second squared. Next, we have to find the normal component of acceleration. We do know the velocity of the particle here, it's 4 meters per second, but we don't know the radius of curvature at x equaling 0. So we have to use this equation to find that. That requires two derivatives of our path function. The first derivative, of course, is equal to 1/2 of x, and at the point x equaling 0, dy dx would equal 0. The second derivative of this equation will give us an answer of 1/2. If I put that into the equation here and evaluate rho, you get the result of 2 meters. Putting that up in here then, and again, as I stated, using 4 and squaring that, we get our answer for the normal component. It's equal to 8 meters per second squared. So like all the other problems where we have motion along a curve, the resultant acceleration will be directed inward, toward the center. In other words, we have an acceleration component this way of 6, another one upward of 8. And so when you add them up vectorially, the resultant acceleration will be directed up this way. And so having finished the problem, now we'll end our review.